Good afternoon, my name is Peter Mendham, I'm CEO of Ascension, and I'd like to talk to you this afternoon about how we take a model-based approach to enabling software portability across a diverse range of hardware in spacecraft systems. So to set a bit of context for our perspective, particularly because our perspective is driven by the market we're operating in, I'll tell you a little bit about us as a company. So we're a small space software company based in Scotland. We sell software products and services across the world. We saw our first mission launched in 2014, and today there are 24 satellites between 3 and 50 kilograms using our software. So from CubeSats through to the smaller end of small satellites, although that is increasing. Our software is used for a really wide range of applications, from EO and remote sensing through to comms and science missions. And the majority of the missions that have been launched are using both our flight and our ground software in combination. The focus of many of our customers is on growing into or expanding their constellations, and that applies to both our current customers and some of the missions we have in development. So we have 8 more due to launch heading towards 2023 that we know about at the moment. We have customers on 6 continents, and we work with those on a commercial basis, but we also collaborate with them and a number of institutional and agency customers on R&D activities. So the kind of market we're operating in has a number of drivers, and these really focus the approach that we've taken with our technology. So I think they're important to summarize, to set the context and to set the requirements for what we do. And I think perhaps the largest is the speed at which we need to operate, with very rapid development times for both individual satellites, but also for the services that those contribute to. Another part is volume, particularly constellations, and the fact that in many cases those constellations are being constantly replenished even when they're operational at an annual or even faster rate. Within a constellation, within a group of satellites, there's typically a very high degree of heterogeneity. So there's large differences, at least at the payload level, but quite frequently at the platform as well, with satellites being built by different manufacturers, and then over time they degrade and also see software upgrades. Software upgrades do apply to the platform, but most extensively to the payloads, with many of the payloads that we're working with being highly complex, with a lot of their functionality being implemented in software, together with use of reprogrammable logic and accelerators like GPUs and machine learning accelerators. So we expect, as part of a mission, for the payloads to evolve significantly functionally over that time. Within both the platform and payloads, we see a very heavy use of COTS hardware from a wide range of vendors, and there is a thriving and competitive ecosystem for those products, with many being available literally off the shelf, so ex-stock. And the focus for all of this is highly automated operations, really aiming for unattended operations for a week at a time. So focusing specifically on the hardware, although the broad kind of functionality offered by pieces of competing hardware can be quite similar, there are differences, and those aren't just in performance or, say, low-level interfaces. There can be substantial differences in the concept or approach that hardware takes. So to take a specific example, looking at 2 CubeSat electronic power systems aimed at the sort of 6U or 10 kilogram CubeSat class, we can look at the AEC ClydeSpace Starbuck power system, which has an I2C interface. It uses a vendor-specific bespoke protocol across that I2C interface and is tightly coupled to the onboard computer. So to do all the command and control is a tight effectively one-to-one relationship between the computer and the power system. As a contrasting case, we can look at the GomSpace P80 power system, which uses a CAN interface. The protocols that it uses are split into 2, with the lower levels of the protocols being a cross-vendor standard called the CubeSat Space Protocol, with the higher level protocols being vendor-specific. And that is designed to operate as part of a network, and importantly, quite independently from the onboard computer, to the extent where it can even be addressed directly from ground. And that is actually expected as part of the way that the hardware is defined and the way that it interacts with the satellite and the overall mission operations concept. So in terms of applying software to this and being able to meet the original challenges, particularly around speed and volume, that poses a very specific challenge for software. How can we create software rapidly and cost effectively and keep risk down in this kind of environment? So we need to focus on software reuse, and to do that we need to find a suitable granularity, suitable size of units of software to reuse. We need to provide ways of integrating those together, and putting that together we need a great deal of flexibility in the way that we can integrate different units of software together and use that to address the diversity in hardware at an architectural level within the software. So we've done that within what we call Generation 1, which is a technology that we've been evolving over the past 8 to 10 years, and it's got 3 aspects to it. It's model-based, which means it has a machine comprehensible representation of the software architecture, and that allows us to build a set of tools to assist with software development, and then other aspects of the overall workflow, such as documentation and PA and QA. The elements that this model works in terms of from a functional point of view are software components, and these are our unit of reuse, and so we can build up libraries of component types and then instantiate those into software to create different forms of software. And a component is a useful unit of reuse because it's accompanied by its documentation and tests within a library. The way that the components interact with each other is that they use services which provide well-defined semantics for the way that they do that and effectively act as a contract. And we use services both at quite a high level for defining how a system can be operated, and at a low level, which plays into our way of managing hardware interfaces and hardware diversity. So concretely, Generation 1 as a technology is a meta-model definition. There's actually a core set of language-independent services we define, as well as some protocol definitions for how those are used between systems. And then we have a cross-platform set of tools, some framework implementations for particular languages, such as an implementation for C, and support for particular target platforms. And we apply this technology both to flight and ground software, but we'll focus on flight here. In terms of how that's structured within a flight system, the focus of the system is on the components, and the vast majority of the functionality within a system is built out of components. So in the diagram you see on the bottom right, it's the top layer where the majority of the functionality and the majority of the code is. The bottom 2 layers are really very thin and just are there to facilitate communications between components and interactions with the very lowest levels of the platform. Components are therefore used to build quite high-level applications, which are typically mission-specific, but also all aspects of the data handling system is built in terms of components, and that's important for us because that can be very different from mission to mission. The communications protocols, communication stacks are built out of components, and even hardware drivers are components. All of the components can be written to be portable across platforms and operating systems. And this is kind of the core to the flexibility. The way that the components interact with each other are through these well-defined services, and those provide this contractual relationship. And that means that provided a component provides a specific service which another component needs to consume, then the component providing that service is interchangeable with others which also provide it. And that gives us a lot of flexibility in the way that we put things together to create different architectures and meet different needs and replace different bits of hardware. Services are themselves defined in the model, and that means that services can evolve over time, which we've seen to be very important. And we have refined services on the basis of real-world usage over the years that we've been working with them. A service is basically a set of operations where each operation has an interaction pattern, such as a request-response pattern, has the potential for typed input and output arguments, and can raise defined exceptions as part of that service operation. The important part about services to highlight, I think, and where their power comes from in many cases, is the concept of how we use a service to carry out operations. And conceptually, we say that a service works with what we call a service object. That's a very vague thing. What a service object concretely is depends on an individual service. But we have a uniform mechanism within the semantics of what we consider to be a service in Gen 1 for identifying the service object that a particular service operation is working with. And that's done using two elements. There is what we call a channel, which is selected using a channel ID, which is defined and specified when you assemble components into a system. And so when you connect up a service at that level, you define which channel it's going to use. A provider will provide a number of channels, and a consumer can then consume one of those or perhaps multiple of those. And that's defined at development time. At runtime, you can select within that. So you may have a channel that you are using, and there may be the option to select multiple service objects on that channel, and you can use a selection ID to do that. And so in different situations, they call for one or both of these. So we can use either one or both, depending on the semantics of the service and also the situation it's being used in. To give a bit more concrete example here, hopefully to try and illustrate what this means, we have our main two I/O services. The packet service is an abstraction of any peer-to-peer communication, whether that be packet or stream based. And the service object here is an end-to-end communications route. And so that can then be selected perhaps mostly at development time, in terms of connecting components to particular routes. And that means then that a specific component type does not need to be coded for a specific situation. What it ends up talking to can be defined by the way it's instantiated and connected. And this is heavily used within communication stacks. And at a low level, some examples of this is RS-42, TCP/IP, and so on. The memory access service is used to abstract away from memory mapped situations, but also mastered buses such as I2C and SPI. And in this case, the service object is a physical peripheral device and things like that. We have a wide range of other services that are also used within the system for other purposes as well. So in terms of where this is coming from, we have developed this as a proprietary standard, and we've done that because we have not found either now or previously any other single solution which meets the full set of needs that we have. And so that's why we've created Generation 1. The reference architecture, particularly for comms and the way that services interact with that reference architecture, draws on our deep experience with CCSDS SWAS. We haven't reused these precise services or the precise service definitions, but the concepts have been very important to shaping the Gen 1 approach. The component and model-based concept draws a lot from the ESA Savoir onboard software reference architecture, and similarly the service-oriented approach is quite well aligned with CCSDS MO. The combined approach here informed our work on the ESA MOS study, and some of the outputs from that also then fed back into our definition for Generation 1. You can draw a parallel with some other technologies that are out there, particular NASA CFS and F', and effectively Generation 1 is a fuller and more evolved solution than either of those in terms of its capabilities and what it offers to the overall workflow. We have been using this approach for 8 years across a large number of missions, and I would say that finding the right abstractions, the right service definitions is hard, and bad ones do lead to inefficiencies or worse. And so that's part of capturing what we do in terms of capturing services in the model. We need to plan for and accommodate change in those over time. There are significant time and risk savings to taking this approach, and when we get service definitions right, it does allow us to still have very efficient software in the way that it operates and performance and things like that. And so we can assemble and configure flight software for a completely new hardware combination in less than an hour, and that's all tooling supported and doesn't involve new code. The focus of Generation 1 is very much on architecture and not behavior. There would be some gains from adding behavioural modelling, but that's not been our focus so far, because the most significant value, especially in the context of hardware subsystems, has been in managing reuse through architectural modelling. And so that's how we've ended up applying an architectural approach to managing hardware diversity in this way. If anyone has any questions, I would be happy to answer them.